All right, so another thing we can do here is, just like capacitors, we can put resistors in different configurations. So for example, here, this light bulb is basically acting like a resistance. So they're acting like resistors because they can provide resistance in the circuit. So those are things like this. Those two light bulbs are connected such that, see, between them, there's only one connection. Only one wire connects them. And then resistor 1 connected to the positive terminal, resistors 2 connected to the negative terminal. That means what we have over there is the example of two resistors connected in series. Okay, so this is known as a series combination. So the currents are the same in all the resistors because the amount of charge that passes through one resistor must also pass through the other resistor in the same time interval. This is condition 1. You can think of like this is condition 1. And this is something I talked about also with capacitors. That means there's going to be an electric field. Remember, electric field going like this. And the same electric field goes through the R1 and R2. That means same charges are moving, right? Same flow of charges moving through resistor 1 and 2. And condition 1 here is, I equals I1 equals I2. Current 1 that comes from the battery is same as one going through the resistor 1 and through the resistor 2. That means this is condition 1 for the series combination or configuration. So there's also another condition which is related to then this delta V. Okay. By the way, here's the circuit element or circuit diagram for that. This is the battery. And battery has positive terminal, negative terminal, right? And then the current, you can see, right, starting from positive terminal, goes around like this. So now you have point A, B, which is across the resistor 1, B, C across the resistor 2, right? And then the current comes back to the negative terminal. Okay. Now, this delta V is then, remember, so this is basically terminal voltage, right? Or the V total. And let's say this voltage is how much given to the entire circuit. So let's say this is 10 volts. That means 10 volts is total available to all the devices. So obviously you can't just give one device 10 volts and nothing for other ones. You have to understand that if you have closed circuit and all the devices are connected, this voltage then will be distributed. And the voltage drop, that means, let's say, how much of this voltage will be available. When we say voltage drop, that means how much of it available and basically used up by the resistor 1 is given as current 1 times resistor 1. Remember, so let's say what I do here is things like this. I put a voltmeter there, and this measures the voltage 1, delta V1. And then I use another voltmeter to measure voltage across the resistor 2. That means, that will be voltage drop. Again, voltage drop means voltage used up by that, second device. And what I have here is how much voltage 1 and voltage 2 basically are used up. That total, right, there's sum. That means going from A to C, right? You can see, right, A connected to the positive terminal, C connected to the negative terminal. That means this VAC is basically the terminal voltage, which is the total voltage. That means you can say that delta V, which is VAC, is equals to then VAB, which is the VAB, in this case, voltage across resistor 1, plus VBC, which is voltage across resistor 2, okay? Or you can write this as delta V1, that means potential difference across resistor 1. So generally, I would just put like this, V total equals V1 plus V2. And this is equals to V1 is then I1 times R1. Then this is then I2 times R2. But if those two are in series, technically I1 is equals to I2 always, okay? But this is then the condition 2. So condition 2, and put it here, right, means that voltage is distributed to your resistors. If they're connected in series, the voltage that battery provides will be given some of it to the resistor 1, some of it to resistor 2. Now, how much will be given to resistor 1? How much will be given to resistor 2? Well, it depends. So let's say, see, the 10 volts is the total available. If the resistor 1 and the resistor 2 are identical, then each one going to be getting half of this. So 5 volts plus 5 volts. That means each one gets exactly half. But what if they're not available? So they're not, sorry, not identical. What do you do if they're not identical? Well, then you use this equation to compare. See, for example, V1 is equals to R1 times I1. V2 is equals to R2 times I2. But since I1 equals to I2, so you can kind of drop those subscripts there, right? That means the voltage 1 and voltage 2 technically depends on only the resistor values. And you can see, right, the one with the bigger resistor gets more voltage. So because this is, let's say, 10 ohms times current, this one, let's say 5 ohms times current, that means this one gonna get double the voltage because it's 10 times I, the other one is 5 times I. That means whatever the biggest, let's say this one is, R1 is bigger than R2, then it's gonna get lion's share. Maybe like, let's say 7 is gonna be given to the R1 and only 3 to R2, depending, you know, what we have. But total sum is still gonna be same as total potential, total voltage that given by the battery. All right, just like capacitors, we can take these two resistors, R1 and R2, and we can say, all right, so this is same as combining them into R equivalent, because this is a simple circuit. So I can, you know, see this R equivalent is same as before. Then what I have here is this. I need to find the equation that gives me this R equivalent, and I can do that by understanding that I have then this equation, right? So see, let's say V total equals V1 plus V2. V total is then R total, which is R equivalent basically, times the total current. This is equals to V1. V1 is then I1 times R1 plus V2. V2 here is I2 times R2. But because condition 1 tells us that I total is same as I1, same as I2, then I can then come and cancel those. I1, I2, and I total cancels. Then what I get here is R total, or you can say R equivalent, is equals to, what survives here is R1, then plus R2. That means equivalent resistance is nothing but the sum of all the resistors in your series. Okay, that means what we get here is equivalent resistance of 3 or more resistors. You can have, like, let's say 2, 3, 4, 10, 100 connected in series. All you do here is add their values to get the total resistance. That means, for example, in this case, if this was, for example, if this was 10 and this was 5, right? 10 and 5, then when I come back here, 10 plus 5, this becomes 15 ohms. That means this is my R equivalent, which is the sum of R1 and R2. Okay. So the equivalent resistance of a series combination of resistors in the numerical is the numerical sum of the individual resistors. So that means what we get here is just adding them together, and it is always greater than any individual resistors. So remember, there are two conditions, right? Condition 1 was that current is constant for the, you know, resistors in series. Condition 2 was then the voltage, you know, a total is the algebraic sum of all the other voltages, right? And then condition 3 then means that resistor equivalent is the algebraic sum of all the resistors. So those are the conditions for the resistors in series. We can also connect resistors in parallel, which means that you take the resistor 1, you take the resistor 2, and you connect them at both ends, just like we did capacitors in parallel. Okay. Now, same thing is here. Here, resistor 1, here you can see right, they are connected at both ends. So both resistors, you can think like now what I have here is, see this point here, let's say, is a point where both of those resistors are connected. Okay. That means they share a common point. So think like this. If I represent it like this, here resistor 1, and here resistor 2. See, let's say if I connect them, you can say, for example, that you can have these 2 points, A and B, and those points A and B are points that they share. And let's say if they're connected to a battery, like let's say here, right? Then point A and B means that they are electrically connected to one another on this end, which is then also connected to battery. and then they're electrically connected on the right side at point B, all right? Which means that if I have a voltage right here, battery voltage, which will be then, let's say, VAB, means that voltage across 1 is also VAB, and voltage across 2 is also VAB, right? Because see, R1 connected to points A and B, R2 connected to points A and B, also is the battery connected to points A and B. That means what we can have here is we can say that both resistors are connected directly across the terminals of the battery. So then the potential difference across the resistors are the same. Delta V equals delta V1 equals delta V2. This is that condition 1 for the parallel combination. Okay, delta V is the terminal voltage of the battery. That means what we have here is if those two connected in parallel, they always have the same potential difference. If they're also connected to the battery directly, right? In this case, they also then have the battery voltage. But then one thing we have here is this. So here's another way of representing that circuit. This point A and this point B now represent what we call junction points, remember? So these are junction points. Means that when the current gets to this point A, see now it has two paths. Let's say path 1, path 2. That means this current I, which is the total current when it gets to point A, will split into 2, right? Will split into 2. So when the charges reach point A, which is the current, right? They will split into 2 parts, with some going toward R1 and the rest going toward R2. That means the junction is a such point in the circuit where the current can split, and then the current, this is the total current, equals I1 plus I2. Now, which one will get most current? Well, it depends on this, right? So remember, the current one is equal to, let's say, I'll do it like this, right? So V1 over R1, current 2, V2 over R2. Well, since V1 and V2 are the same, then current 1 and current 2 basically depends on R1 and R2. In this case, the one with the smaller resistor gets the most current. That means technically you can think of it like this. The current is most where the path is less resistive. Most of the current goes to the less resistive path. All right, so here's then what we get. So then the total current equals I1 plus I2. What is I1? Is voltage across resistor 1 divided by resistor 1 plus voltage across resistor 2 plus over resistor 2. Basically Ohm's law, right? V over R for each one of them. So I1 is the current in R1, I2 is the current in R2. So then how about equivalent? Well, I can again combine them into a single resistor, and I can say that what I get here is then the single resistor has this R equivalent resistance. How do I calculate that? Well, I calculate that remembering this equation, right? I equals I1 plus I2, which was, remember, the condition 2. I is the total, so then this is equals to V total over R total. Then I1 is V1 over R1. I2 here is V2 over R2, basically rearranging this equation into that form. But condition 1 tells us that V total is same as V1 is same as V2. That means I can cancel them. And if I cancel them, and I get this equation then. 1 over R equivalent is equals to 1 over R1 plus 1 over R2, which means in this case, R equivalent is less than R1 or R2. Because you then decrease the total resistance in the circuit. Okay, so the equivalent resistance over resistors in parallel is given by 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. And then the inverse of the equivalent resistance of the 2 or more resistors in a parallel combination is equal to the sum of the inverses of the individual resistances. The equivalent resistance is always less than the smallest resistance in the group. This is also always going to be true. That means whenever you're calculating the equivalent, you're then always going to get less than even the smallest, let's say, resistor you have in the group. All right, so then what we get here is this. you're going to get then resistors in series. So let's say here, R1, R2, R3. Let's say, okay, so let's say this is 10, this is 10, this is 10. R equivalent, then sum of that. In this case will be 30, and I can represent this with just a single resistor with a 30 ohm resistance. I can simplify this. Or we can have something like this, R1, R2, R3. I can again combine them and have R equivalent using this equation, right? So R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3 to the -1. Okay, so I can combine and represent it like this. Well, what if you have something like that? You can have a combination of resistors in series and parallel. See, what we have here is there's R2 and R3 in series, in parallel, and this combination is in series with R1. So then what I will do here is I say, okay, so here's R1, and then first I find the combination of R2 and R3. So I have like R equivalent for those. And then I combine those two together into just a single resistor, which is going to be R1 plus R equivalent because, you know, they are in series. It means you can, again, simplify. Or you have something like this. You have those two in series, and that combination is in parallel with this guy. So what we do here is, for example, if this is 10 and this is 10, then you can simplify and say at the top, you have equivalent of 20 because you're just adding them together. At the bottom, this R1, maybe let's say it's also 20. So let's say this was 20 to start with. Then you combine those two together into equivalent, so 20. And then the bottom one is 20 already. And then remember, in parallel, if you have two identical, then their equivalent is exactly half. So then this is going to be then 10. You can try to then apply this equation to that and see yourself. That means you're always going to get an option to basically combine several combinations and things like that together. All right, so let's solve some problems. 3 resistors are connected in parallel as shown. A potential difference of 18 volts is maintained between points A and B. Calculate the equivalent resistance of the circuit. Then find the current in each resistor and calculate the power delivered to each resistor and the total power delivered to the combination of resistors. All right, so let's start with, identifying what we have. So this is our, a voltage, right? Potential difference, so delta V, this is V total. And what I have here is this. I have 3 resistors, 3, 6, and 9, that are connected in what type of configuration? What do you guys think? Give it a minute and think about it. Well, you can pause and think about it, let's say. So here's they're connected in parallel. Okay, they're connected in parallel, even though it shows over here, but you should be able to recognize it yourself. So that means, for example, see this point A is common for all of them on one side and point B common for all of the side. That means what you have here is that V total is equals to V1 equals to V2 equals to V3. That means they all have the same potential difference of 18 volts. And then we're given their values of the resistors, right? 3, 6, and 9. That means for part A to calculate equal, let's say equivalent resistance in the circuit, in this case, right? All I have to do here is combine them. So R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3 to the -1. So then this is then 1 over 3 plus 1 over 6 plus 1 over 9 to the -1. And we're going to get R equivalent of 1.64 ohms. That means in a way I can combine this to be just one resistor of 1.64 ohms connected across 18 volt battery. Basically it means just that. Now it says find the current in each resistor. That means, what I can do here is this. See if I use these values, 18 and 1.64 ohms, I'm going to get a total current. But because this is a junction point, the total current I will be split into 3. So for part B, what I can do here is I can then calculate I1 from taking V1 over R1. I can do that because at this point we're given all of those values, right? it's going to be 18 over 3, which is going to be then 6. I2 is going to be then 18 over 6, which is going to be 3 amps. And I3 is going to be then 18 over 9, which is then 2 amps. You can also calculate total from here. 6 plus 3 plus 2, right? So you're going to get 11 amps total. All right, so point C, part C then says calculate the power delivered to each resistor and the total power delivered to the combination of resistors. All right, so in this case, what we do here is we can just use the one of this power equation, right? And you can just calculate them any way you want. So let's say if you do IV, right, it becomes P1 equals I1 times V1, for example. I would just, maybe do that. So I1 here is 6 amps. V1 here is 18. So 6 times 18, right? You should be able to, well, sorry. I1, yeah. So 6 times 18. So we should get 108 watts. P2 here is I2 times V2, right? So let's say this is going to give us I2 is 3, V2 here is 18. So we're going to get 54 watts. Same thing with P3, we're going to get 36 watts. And so basically, what I can do here is just, I can just add them together to get the total power that delivered to the circuit. So let's see. All right. So one more example. So it says 4 resistors are connected as shown. Okay, so on the slide you might be able to see that, but what I have here, I'm going to just draw it for you here. So here's one resistor, 8 ohms, and here's another one, 4 ohms. So, and then this is, let's call this point A, and this is point B, because point B then has 2 resistors, 6 ohm here, and 3 ohms here connected. And then this goes to point C. So this is the configuration we have. Let's find the equivalent resistance between points A and C. All right, so let's do that. Let's do part 1, which means the total here. So you look at those two, well, they're connected in series. I can combine them and I can have 8 plus 4, this is 12, sorry, 12 ohms. And then I can see that those two, 6 and 3, are connected in parallel. That means I need to find their equivalent. So I can put here, this is their equivalent. And I do that by using, remember, one of those shortcut equations. So I can say R equivalent, if I have 2 resistors in parallel, I can say this is R1 times R2 divided by R1 plus R2, just like we had for the capacitors in series, if you remember. So R equivalent equals then 6 times 3 over 6 plus 3, which is then 18 over 9. So this is just then 2 ohms. Okay. So then from here, I can then say, okay, so then this is 2 ohms. And I combine those two together in series, because they're in series, right? This becomes then 14 ohms. Okay. That means, let me see, did I do this correct? 8 and 4. Yeah. So the total equivalent is then 14 ohms. That means going from point A to point C, I have 14 ohms. Part B says, what is the current in each resistor if a potential difference of 42 volts is maintained between A and C? Let's go back here. That means here, think like this, there's a battery there of 42 volts. So now what do we mean? So how do we then get, the current in each resistor? Well, here we have to kind of look at it in terms of what we're given. Okay, because what I can do here is assume that this picture here is equivalent to this one here with 42 volts. See, all those resistors together is same as this one resistor of 14 ohms connected to the 42 volts, right? That means then I can use this to calculate total current, which is then going to be total voltage, 42 volts, over the total resistance, 14 ohms. And that will give me 3 amps. Okay, that's the total. That means that's the current coming from the battery. Okay. Now, look at then this current. So this current is going to go like this, go through 8, go through 4, and then come to the point B. Which means that as this current goes through 8 ohm resistor and 4 ohm resistor, is the same current because there are no junction points, you know, from the positive terminals to point B. It's just one straight path. That means current through 8 ohm resistor is same as current through the 4 ohm resistor is same as total current, which is then 3 amps. Okay, remember one thing, right? That resistors in series have the same current, you know, they have the same current. Those two in series, they have the same current, and because they're connected to the battery, they have the same current as the battery. All right, so then when the current gets to this point B, then it splits into two. So there's current 6, I6, and there's current I3. Now the question here is, how do we find those ones, right? How do we find those ones? Well, in this case, there are several ways we can do. Right? So in this case, there are several ways we can do to go around that. That means there's a way of finding in terms of, let's say, how we can get the current over there for I1 and I2. And this, like, let's say one way is to do a ratio. Because remember, what I have here is this, right? Voltage across 6 is the same as voltage across 3, right? Sorry. Voltage across 3. Because see, both 6 and 3 ohm resistors connected between B and C. That means, you know, both of them have the same potential difference. Okay. Now, what I get here is this then. Voltage across 6 using Ohm's law is the current across 6 times then 6 ohms, right? And then what I get here is then voltage across 3 is basically means that, or sorry, it's probably easier to do it like this. So let's say voltage across 6 is equals to voltage across 3. Probably easier to kind of understand this rather than do ratio, because they both have the same potential difference because they're in parallel. Then this one is I6 times 6 because it's the, resistance. This one here is I3 times 3, okay? Which means that if I'm looking at this, right, then I can see that if I cancel this, then this get I3 is equals to 2 times I6, okay, 2 times I6. That means current through the resistor 3 ohms is double the current through the resistor 6 ohms, because remember, those are sort of like, let's say, least, the current, most current goes through the least amount of, let's say, resistance. All right, so that means I have this, right? I3 equals 2 times I6. Remember then, the current that gets to point B is the total current. So then when the current gets to the point B, it's total current. It then splits into two, right? Becomes current going through the 6 ohm resistor plus current going through the 3 ohm resistor. But then what I'm saying here is this then. Current through the 3 ohm resistor is 2 times, is the double to the current through the 6 ohm resistor. That means I'm substituting this guy, okay? Means that total current is equals to I6 plus 2 times I6, which is then 3 times I6, which means I6 is total current divided by 3. Total current was 3 amps divided by 3. That means it's 1 amp through the top resistor 6 ohms. Well, since I3 here is then equals to 2 times I6, means then I3 then is equals to 2 amps, okay? Which means then I6 plus I3, right, give you the same total as, the total one, which is, you can say 2 amps plus 1 amp, give you basically 3 amps. All right.